I'm Doug Fern. This is my take on music recording. In the previous episode of this series, I talked about some of the basic electrical and electronic terms and how they are interrelated. I will add a couple more here, but be aware that these are just the fundamental components and concepts. Anything deeper is beyond the scope of this discussion. We have talked about voltage, current, wattage, and resistance, but the next two are only applicable in an alternating current situation. Practical electricity comes in two distinct forms: alternating current and direct current, AC and DC. DC is what comes out of a battery, and it was the first type of electricity that scientists and researchers studied. It was the only electricity they knew. DC is also what powers all our electronic equipment internally, and it's the simplest to understand. Take a battery. It has two connections, labeled positive and negative. Current has to flow from one connection to the other to complete a circuit. A flashlight is about as simple as it gets, and it uses DC. The first experiment I ever did with electricity was when I was 6 or 7 years old. This was in the days when flashlights used incandescent bulbs, but the same principle applies to modern LED flashlights. I wanted to figure out how a flashlight worked, so I took one apart. Inside were two batteries, which are more correctly called cells. The two D cells inside were stacked one on top of the other inside the handle part of the flashlight. At the top of the flashlight was an assembly that had a small light bulb. You could see it through the glass lens of the flashlight. It was in a socket because incandescent bulbs had a finite lifetime, measured in tens of hours. Most flashlight bulbs stopped working if you dropped the flashlight. Whatever the cause, you had to periodically replace the fragile bulb. Incorporated into the handle of the flashlight was a sliding switch, which turned the light on and off. It was difficult to see exactly how that switch worked, but I plowed ahead in my quest to understand this device. I deduced that the connection to the end of the bulb sat directly on top of the battery positive terminal. That was one connection, and I thought that the other end of the battery, the negative end, should go back to the other connection to the bulb. I didn't have any wire, but I found a paper clip, and with the bulb on the top of the battery and the paper clip connecting the bottom of the battery and the shell of the light bulb, it worked. It is the simplest circuit there is, but it got me started. The flashlight circuit had just 3 parts: the battery, the bulb, and a switch. A switch intentionally interrupts the circuit by disconnecting the battery from the bulb. In the off position, the switch is said to be open, and when the switch is on, it is said to be closed. In our everyday experience, something closed, like a door, stops us from going through. We can only go through an open door. But confusingly, a switch that is closed allows electrons to pass. It's more like a drawbridge than a door. In fact, the schematic symbol used in circuit diagrams shows a switch as something that resembles a drawbridge. I also observed that with just one battery, the light was dim. Stacking another battery on top increased the bulb brightness. 3 batteries made the bulb very bright, but it burned out the bulb in seconds. All electronic devices have limitations on the amount of voltage and current they can handle. A bulb, or LED for example, must be rated for the expected voltage. A switch has to be designed for the expected amount of voltage and current it has to handle. This was a series circuit. Each battery added its own voltage to the stack of batteries. One cell provided about 1.5 volts. 2 of them in series resulted in 3 volts, and 3 of them gave me 4.5 volts. The bulb was rated for 3 volts, and quickly burned out at 4.5 volts. The amount of current can be thought of as the amount of work being done, in this case creating light. In a series circuit, the amount of current measured at any point in the circuit will always be the same. Another form of circuit connects devices in parallel, and it's called a parallel circuit. Your house or studio has all the electricity-using devices connected across the same supply of incoming voltage. Every device gets the same voltage. In a typical U.S. house, that would be 120 volts. But each device may use a different amount of current. In a parallel circuit, the amount of current can be determined by adding up the current of each device. A typical electronic circuit may have both series and parallel devices using the voltage. Sometimes one configuration is needed for a particular purpose, and sometimes the other configuration is best. Actually, most circuits contain a hybrid of series and parallel circuits, and understanding how the current flows through a maze like that can require a lot of calculations, but only simple algebra is needed. If you put two batteries in series, their voltages add up. But if you put two batteries in parallel, you get the same voltage as one battery, but the current available is doubled. As a kid, I learned what came out of the wall socket in my house was AC. What's the difference between DC and AC? Well, for some things like an incandescent light bulb or a toaster, it doesn't matter if it's AC or DC. However, for most electrical and electronic devices in our lives, it makes a big difference. And connecting a device designed to run on DC to a source of AC won't work. In fact, it may blow up, or at least blow a fuse or a circuit breaker. The same problem exists if you try to connect a DC source to a device that needs AC. If electronics need DC, why is power distributed in the AC form? Before I answer that question, what exactly is alternating current? In the earliest days of electrical distribution, the system used DC. There was a great battle between Thomas Edison, whose power plants delivered DC to its customers, and several others, including Nikola Tesla and George Westinghouse, who thought AC was a better system. And the latter were right. First, we have to understand the relationship between electricity and magnetism. Early researchers discovered that current flowing through a wire created a magnetic field around that wire. It was weak, but enough to cause a compass needle to move. A permanent magnet, like in a compass, retained its magnetism indefinitely. Not forever, but for a very long time. You could also create a magnet by winding multiple turns of insulated wire around an iron core. That's an electromagnet. Its properties were identical to a permanent magnet, except for one thing. It was only a magnet when connected to a source of DC power. As soon as the current stopped flowing, the iron core ceased to be a magnet. The first practical use of electricity was the telegraph, and it used electromagnets. When the current was flowing, the electromagnet caused a nearby piece of iron to be attracted to it. That piece of iron was on a hinge, and when pulled to the electromagnet, it clicked. That click sounded out the dots and dashes of Morse code. The switch, in this case, was a telegraph key. The same principle is at the heart of much of our modern electrical world. One common example is the relay. The term was applied to an electromagnet that, when powered, caused an attached switch to close, completing a separate circuit. The separate circuit had its own battery. This was used to take a weak telegraph signal and essentially amplify it so the telegraph range was extended. The relay relayed the message to the next set of wires. We still use that term. Many of our current electronic devices in the studio use relays to remotely control something. In the DW Fern microphone preamplifiers, for example, we use relays to modify the path of the audio signal through a pad or to turn on 48 volts for phantom powered mics. We could just as easily use a switch to do the same thing, but the relay allows us to put the actual switching part right where it needs to be. Otherwise, a microphone-level signal would have to come to a front panel switch, which could compromise the audio quality. You can probably think of dozens of other pieces of control room equipment, or in your house, that use relays. In a household electric oven, for example, a relay is used to switch on the high current heating element the oven needs, while the actual switch on the stove can be very small and inexpensive, since it only has to handle the very low current needed to actuate the relay electromagnet. Another reason for using a relay is that they can be sealed devices with gold contacts, so the connection is always perfect. No oxidation to introduce resistance, as well as noise and distortion, into the audio. You know how rotary switches can become noisy or intermittent, which happens when the contacts in the switch become oxidized. When you move a front panel switch on any of our products, you can hear a tiny click deep inside the equipment. That's the electromagnet of the relay pulling in the contacts that do the actual switching. What does this have to do with AC? Well, the electromagnetic property of current flow can be used in a transformer to change the voltage, either to a higher or lower voltage. It does this because there are two separate windings of wire on the common iron core. The ratio between the two windings tells us how the voltage will be changed, higher or lower. The magnetic field of the transformer core forms and collapses at a rate dependent on the mains frequency, either 50 or 60 hertz. When the magnetic field is changing, the electrical current causes the applied voltage to be induced into the other winding on the core. In an ideal transformer, all the power in the primary winding will be transferred to the secondary winding. Good transformers are very efficient. Any wasted energy is converted to heat. But if you put DC into the primary, it would just form a magnet. There would be a very short blip of current going from one winding to the other when the source of electricity was started or stopped, but that would not be useful. A transformer only works when the voltage is changing, and an AC voltage is constantly changing. It turns out that a generator, a device to convert mechanical energy into electrical energy, actually produces that constantly changing voltage, AC. And if it is designed properly, the output of the generator produces a sine wave. A sine wave has a specific definition based on trigonometry, but we don't need to get into that to understand the principle. We need to know, however, that a sine wave has both a positive and a negative portion of each cycle, centered on a baseline where the voltage is zero. The voltage starts at zero, increases to a positive peak, and then diminishes, passing again through 0 volts. But it doesn't stop there. The voltage continues to decrease into the negative voltage range, hits a maximum negative value, and then starts to increase again. It continues this up and down path for as long as the generator supplies power. A perfect sine wave has a perfect shape, and the negative and positive portions are exactly the same voltage, and the waveform is symmetrical. All sounds are composed of sine waves. All sine waves have a particular frequency. It's a musical note, and all musical instruments produce a sine wave at a frequency that is correct for the scale of the instrument. But instruments do not produce pure sine waves. Sine waves are not very interesting to listen to. Notes from any musical instrument include harmonics, multiples of the main or fundamental frequency. All audio signals are actually AC, although we do not generally call it that. For a generator, we need a pure sine wave. That works best for transformers in the electricity distribution system. It's not that important for audio transformers. They work fine with the complex waveforms of audio. As a practical example, suppose we need to convert our incoming mains power to a lower voltage to run our circuits. In solid-state equipment, that is generally less than 50 volts. If we have a transformer that has the proper ratio of turns on the primary and secondary, we can change the 120 volts from the AC outlet to the lower voltage we need. It works great, and it is at the heart of everything electronic. The power distribution system has a different requirement. We have to get the power from the generating plant to the customer as efficiently as possible. We know that all conductors have resistance, which is the opposition to the flow of electrons. We also know by Ohm's law that the greater the current, the more power is lost in the resistance of the wires. And since the wires from the power plant to your studio could be hundreds of miles long, there is a lot of loss. To reduce the loss, we could use fatter wires, which have lower resistance and therefore lower loss. But there is a limit to the size of wires we can use. If our wires have to carry thousands of amps of current, the wires would have to be gigantic if we used 120 volts. The solution is to use much higher voltage. If we double the voltage, the current in the wires is dropped by half. That means we can use thinner wires and still have acceptable loss. The actual voltage on those long-distance transmission lines is very high, measured in thousands of volts or even hundreds of thousands of volts. It is an elegant solution to the problem. But we can't use 100,000 volts in our home or studio. At that voltage, it is easy for electricity to jump from one conductor to another, often over many feet. It would be exceedingly dangerous and impractical. So along the path to your facility, the voltage is periodically reduced through transformers. Those transformers may have to supply an entire town, so they are big. You can see them in electrical substations. As the power gets closer to the consumer, each transformer only has to supply a few homes or businesses, so they can be much smaller. They are still big, but small enough to be placed high on a power pole. They look like a cylinder. You see them everywhere. Or in areas built more recently, they may be on the ground in a metal enclosure, or even underground. Transformers are also used extensively in our studio gear, not just to convert the incoming AC voltage to what the equipment needs, but also for audio. Those transformers are much smaller, small enough to fit inside a handheld microphone, for example. The amount of power the transformer has to handle largely determines its size. Mic-level audio is very low in voltage, measured in thousandths of a volt. The largest transformers in our studio might have to handle a much higher voltage and a lot of power, such as in a vacuum tube power amp to drive your control room speakers, or inside a guitar amplifier. Regardless, all transformers work on the same principle. Power transformers only have to work with a fixed frequency, 50 or 60 hertz, but audio transformers have to work over at least a 10-octave range. The 20 hertz to 20 kilohertz our hearing is capable of detecting. That's a much more demanding application for a transformer, and the design of audio transformers is complex. I should mention that solid-state circuits can be designed that duplicate the role of an audio transformer. This offers a great savings to the manufacturer. Quality audio transformers are very expensive, and there are only a few companies that specialize in producing the transformers we need in the studio. A transformerless input or output is much cheaper to build and takes only a fraction of the space a transformer would need. Whether this is progress or not is a matter of opinion, but there is no question that it reduces the cost of equipment that goes the transformerless route. The transformerless concept only works at very low voltages, so for power distribution, we still rely on large transformers with an iron core. In the power supply of our equipment, we must convert the mains voltage to a lower voltage for the circuitry, or a higher voltage in the case of vacuum tubes. But those audio amplifier circuits need DC, not AC. The output of a transformer is still AC. We need a way to convert AC to DC, and the device that does that is called a rectifier. The earliest rectifiers use a very simple vacuum tube called a diode. Those are still used in guitar amps, but today most rectifiers are solid state. They are still called diodes, and all diodes work basically the same way. A diode is like a one-way street for electrons. Depending on the orientation of the diode, either only the positive portion or only the negative portion of an AC waveform is allowed to pass. The result is closer to DC, but not in a form we can use in our equipment. What we have done with the rectifier is cut off the negative portion of the AC waveform, leaving only the positive part. The result is called pulsating DC. It has some of the same characteristics of both AC and DC. That's not useful. We need pure DC for our audio circuits. We have to filter the pulsating DC and try to make it as pure as possible. And we filter the pulsating DC with one or more capacitors. Capacitors have several interesting and useful properties. For one thing, a capacitor stores electricity, sort of like a rechargeable battery, but only for a very short period of time. If we design our filter properly, the stored energy is released exactly when needed to fill in the gaps of the pulsating DC. The result is closer to pure DC, like what comes out of a battery. But filtering is never perfect. There is always some component of the original AC waveform present. That imperfection is heard as hum, which is either at the same frequency as the mains frequency or an octave above. Good design minimizes this hum to inaudibility. The frequency of the hum depends on the type of rectifier circuit used. A more complex rectifier, using multiple diodes, is more efficient and produces mostly the second harmonic. That would be either 100 or 120 Hz, depending on whether the mains frequency is 50 or 60 Hz. But that's not all a capacitor can do. It can block DC and permit AC to pass, which is vital in amplifier circuits in order to couple one stage to the next. The DC voltage that an amplifier circuit needs to operate must be blocked from entering the next amplifier stage, or the output. Otherwise, the electronic device would not operate properly. A capacitor can also be used in conjunction with a resistor or an inductor to form a frequency-selective element. That forms the basis of equalization circuits. An inductor is simply a coil of wire around an iron core. With DC applied, it would simply be an electromagnet. But with AC, it has properties similar to a capacitor, but everything is opposite. When an inductor and capacitor are connected together, they can form a resonant circuit. We know what resonance is. An example of resonance is when an audio frequency excites an acoustic space. At the resonant frequency, that frequency is emphasized and all other frequencies are diminished. That is also how musical instruments work. When you play a single note on a guitar, that note is heard and all others are suppressed. In the case of musical instruments, the resonant frequency is determined by the length of the string and its tension, or by the volume of the hollow part of a wind instrument. We can duplicate that effect in electronic circuits, and that's how analog synthesizers work. Resonance is another fundamental property that exists in electronic circuits, and we will start with that in the next episode. Thanks for listening, commenting, and subscribing. I know this episode departs from my usual discussion of practical matters in the studio. Let me know if you find this valuable. You can reach me at dwfern@dwfern.com. This is my take on music recording. I'm Doug Fern. See you next time.